Motion. This is my first video about motion and graphing motion, it's called, because we're going to start with displacement time graphs. I do a nice little experiment with my students. Imagine you walk in a straight line at a constant velocity. Every 5 seconds you drop a beanbag on the floor, then you measure the distance from the start at each point, and then you can plot a displacement time graph. And if you notice there, if you do a fast walk, you get a steeper graph. A slow walk, it's less steep. Let's make it clear that the difference between displacement and distance. Displacement is the distance traveled in a certain direction. Imagine I go for a wiggly walk. If I end up 200 meters east of where I started, then my displacement is 200 meters east. The distance I traveled may well have been 300 meters. My velocity is displacement over time. So if the journey took 100 seconds, then my velocity will be 200 divided by 100, which is 2 meters per second east. My speed, it doesn't matter what the distance was, speed is distance over time, so my speed will be 3 meters per second. From now on, I'm just going to talk displacement. If it's distance in a certain direction, then it's displacement. Now, this object is slowing down, so how do we find its velocity at a particular time? And what we do is at that particular time, you mark it on the graph, on the curve, and then you get the gradient. And the gradient tells me the rate of change of displacement at that time. And the rate of change of displacement is ds dt. V equals ds dt. I'm going to use S for displacement. And this is what we call the instantaneous velocity. It's the gradient of a tangent at that point. If ever you have to do it accurately. Draw a nice big triangle to get the gradient of the tangent. Of course, if you know the equation for displacement against time, you could always differentiate it. Okay, a man falls off a cliff. This graph shows how the distance he has fallen varies with time. How far has he fallen after 1 second? What is his average velocity in the first 1.6 seconds? And then what is his velocity at 1 second? Now, I know you can't really draw a tangent to the point because you're probably watching this on a computer or a mobile phone or whatever, but the answers are, okay, 5 meters, 7.9 meters per second, and 9.8 meters per second. And I cheated because I knew his acceleration was 9.8 meters per second squared. Okay, here are some velocity time graphs. The first object is traveling with a uniform velocity. Its acceleration is 0. Then we have a uniform acceleration from rest, a uniform acceleration not from rest, from an initial velocity, and then the last one is a uniform deceleration. Okay, acceleration is change in velocity over time. A equals v minus u. Now, v minus u over t, that's fine. If the acceleration is not uniform, then this equation would tell us the average acceleration. If the acceleration wasn't uniform, here's a very important graph which you should recognize. It's like if you jump out of an aeroplane, your velocity, your vertical velocity against time would look something like this. How would you find the acceleration at an instant? Well, acceleration is dv dt. It's rate of change of velocity. And so what you do is at that point on the graph, you draw a tangent and you get the gradient of the tangent, dv dt, rate of change of velocity. The area under a velocity time graph tells us the displacement of the object. Pretty straightforward on the first graph. I mean, displacement is velocity times time, so it's the area of the rectangle. And then for all of the other graphs, it's the sum of lots of little rectangles. It's the area under the graph. Here's a question for you to have a go at. It's a velocity time graph for a bus journey. It's in 4 stages, and in each stage, 1, 2, 3, 4, I'd like to know the acceleration and the distance travelled. And the answers are that.